Hello, everybody. Before beginning, I would like to thank to everyone involved in the organizing the symposium and giving me the opportunity of this talk. Unfortunately, I am too away from Georgia. This time, I could participate remotely. Maybe, hopefully, next time we will be together. My talk is on the PhD on master thesis of my graduate student Rehan Asupeoğlu. In his thesis, he synthesized polyacrylic acid and methacrylic acid based graft copolymers through the graft-through approach, and he defined the graft copolymers using thermal and spectral techniques. And then he fabricated some nanofibers of the graft copolymers using electrospinning. Let's see how he did this and what he discovered. Yes. As we mentioned, graft copolymers were obtained graft-through strategy. What is it? Graft-through strategy, it's a polymerization strategy to obtain graft copolymers using a vinyl monomer and a macromonomer with vinyl end group through free radical polymerization or other controlled polymerization techniques. Since the feature of the graft copolymer are mainly dependent on the macromonomer, its chemical structure, its length, polydispersity, and reactivity determine the features of the graft copolymer. So we need to focus on the macromonomer. Macromonomers are not only used for obtaining graft copolymers, they can be used itself as surface modifier, stabilizer, compatibilizer, emulsifier. Also, they can be used as components of block copolymers or in other graft copolymers. So we used macromonomers in the study. We did obtain our graft copolymers. We used hydrogen transfer polymerization. It's a polymerization method using some acrylamide or acrylic acid or their derivatives and some strong base or good nucleophiles as initiator. Polymerization undergoes aprotic solvents. During the polymerization, Michael type addition occurs. That's why we obtain heterochain polymers, not addition polymerization product with CC bond backbone. So its yields are potentially biodegradable and biocompatible due to the presence of ester amide or ether functional groups in their backbone. Although it has some limitations of lower molecular weights to use in practical application, in the study we use this disadvantage as advantage to obtain another polymer for further polymerization through graft-through strategy. In this study, we used acrylamide and methacrylamide as monomer to obtain, respectively, polybetalanine and polyalpha-methylbetalanine. We used sodium tertiary butoxide. is initiator deliberately because the initiator is very strong and weak nucleophile. That's why at the initiation stage we target to obtain vinyl end group by abstraction from hydrogen atom from amide group at initiation stage. That's why we could be obtain a macromolecule with vinyl end group. So after polymerization, we got FDR spectra, which both of the spectra showed us secondary amide bonds of amide carbonyl and NH stretching bonds. To make sure we obtained NMR spectra, which has vinyl protons of metacolite groups, also shows the formation of macromonomer at the end of the polymerization. To make sure, and we obtained multi-mass spectra of both product. As shown, the degree of polymerization is about same, about 20, because the center of the spectrum has a mass of 1,400 and like that for both. And the mass separation between the signals are corresponding to the monomer used for beta-alanine, for acrylamide, 71 Dalton, for 75 Dalton for metaclamide. And randomly selected single, here 1088 Dalton, corresponds to the integer of repeating unit plus sodium ion adduct mass. Similarly, the signal corresponds to the integer of repeating unit of metaclamide or alpha methyl beta-alanine plus sodium atom. So this results indisputably proves the formation of macromonomer with vinyl end group, because the if any adduct is available on the chain, we need to see additional mass to explain the each signal. After making sure that we have macromonomers for further polymerization or grafting through approach, we used acrylic acid as monomer and these two macromonomer as macromonomer to obtain branches. After overnight polymerization, we got viscose solutions, and after pouring the reaction mixture into the excess methanol, some precipitation occurred. They are unreacted macromonomers. As we know, the polyamides are not soluble in methanol. So we choose this solvent to separate, to purify the graft copolymer. After filtration, we lyophilize the solution to obtain graft copolymer. After obtaining graft copolymer, we run the FDR, and we observe that each spectrum has both acrylic acid bonds and secondary amide bonds coming from beta-alanine and methyl beta-alanine. But it's interesting that the comparison of the carbonyl bonds or NH bonds, it can be predicted that the grafting of methyl beta alanine is higher than those of beta alanine. It's just prediction. It's a not quantitative analysis, but it's a prediction. When we see the NMR spectra of the beta-alanine grafted polyacrylic acid, as we see both beta-alanine signal proton and polyacrylic acid protons. The elemental analysis have been performed and the nitrogen content has been obtained, and after calculation, degree of polymerization is found as 13 by mass, 13% by mass. The same procedure applied for methyl beta-alanine grafted polyacrylic acid, and both the beta-alanine, methyl beta-alanine protons and the acrylic acid protons were observed in the spectrum. And after elemental analysis, we determined the nitrogen percentage, also grafting of methyl beta-alanine, is higher than the beta-alanine as shown. It's 23% by mass, consistent with the FTIR results. So we continue to synthesize graft copolymers using methacrylic acid and this 2 macromonomer. The same reaction routine and the same purification routine. After that, we obtained the FTIR spectra. Similarly, the intensity of methyl beta-alanine bonds higher than beta-alanine bonds, amide bonds. So we can predict again that methyl beta-alanine grafting is easier, is quantitatively higher than the beta-alanine grafting. So the elemental analysis proved this prediction, as shown by mass. Degree of grafting beta-alanine is very lower than the methyl beta-alanine one. After being sure that the graft copolymers have been obtained successfully, we aim to obtain thermal properties of the graft copolymers by thermogravimetric analysis and DSC, differential scanning calorimeter. As you see, the TGA and derivative curves, polyacrylic acid graft copolymers have similar pattern as shown and in each other. Also, polymethacrylic acid copolymers have similar pattern in each other. The difference comes from the branches, the content of branches. As we know from literature, the polybeta-alanine and polyalpha-methyl beta-alanine decomposes thermally at about 300 and 350 degrees centigrade. That's why these mass changes attributed to the branches and the amount of the mass loss are close to the data obtained from elemental analysis. So the prediction, the approaches seems to be correct. To see the relationship between the methylbetalanine and betalanine content of the in the graft copolymer, as shown, the betalanine signal is smaller than methylbetalanine for polyacrylic acid graft copolymer. It's also valid for methacrylic acid graft polymer. These results also confirmed by elemental analysis as shown in the table. Moreover, DSC analysis have been performed to see the TG value of the graft copolymers. Unfortunately, we couldn't observe TG for methacrylic acid graft copolymers, but we obtained data for acrylic acid graft copolymers, and these TG values are lower than the homopolymer of polyacrylic acid as expected. You know, after grafting, this type of copolymers experience lower glass transition temperature because of, you know, free volume increase. After completing the characterization, the other goal of this study was obtain nanofibers of this graft copolymers through electrospinning. Reha applied several electrospinning parameters like voltage, needle size, and needle target distance to obtain homogeneously distributed nanofibers. And after analysis of electrospoon mats with SEM, we were able to obtain relatively homogeneously distributed nanofibers. And as shown, their diameter and the standard deviation after analysis, we can say that almost there is no beads on the mat. Also, relatively homogeneously distributed nanofibers could be obtained. Unfortunately, we couldn't get homogeneously distributed nanofibers from the methylbetalanine grafted methacrylic acid graft copolymers. As shown in the figure, we applied different parameters here, and almost there is no regular nanofibers obtained, possibly due to the low solubility of the copolymer in methanol, because as you remember, the high methylbetalanine content, about 27 by mass, have been obtained by elemental analysis. We know that the increase in the amount of polyamide causes the solubility of the polymer, the graft copolymer in methanol will be decreased. So we had to use dilute solutions of methanol for electrospinning, and that caused to failure of fabrication of nanofibers. We performed energy dispersive X-ray spectrometry analysis with the conjunction with the SEM analysis to observe the mass distribution, elemental distribution of the surface of the mats. As shown, the nitrogen atom is an indication of the grafting, very well distributed, homogeneously distributed on the surface of the nanofiber mat. And the quantitative analysis of nitrogen by this method give the results very close to the results obtained from elemental analysis. This is also valid for another copolymer, polyacrylic acid graph methylbeta-alanine, polymetacrylic acid graph beta-alanine. The results obtained from ADX analysis compared with the elemental analysis here. As shown, they are very close to each other. For three types of graft copolymer. After seeing this proved grafting success, we can conclude that we obtained 4 types of graft copolymer based on polyacrylic acid, metacrylic acid, and beta-alanine and alpha-methyl beta-alanine. This is the first time have been synthesized for by the graft-through strategy. The S-spoon mats of 3 copolymers, I mean, except the polymetacrylic acid graft methyl beta-alanine, exhibit cylindrical, smooth, and bead-free nanofibers with diameters ranging from 70 to 1,000 nanometers, depending on the electrospinning parameters. A combination of the copolymerization based on graft-through strategy and electrospinning provided a practicable approach for the preparation of nanofiber mats with tunable chemical composition. The incorporation of alternative branches like beta-alanine, methyl-alanine in this study or another pentane groups may be applied for another system to tune mechanical, thermal, and processability properties of some other homopolymers, not acrylic acid or metacrylic acid, for specific applications such as drug delivery, tissue engineering, or environmental remediation. Thanks for your attention. I need to mention that the study has been supported by the Ordu University Scientific Research Coordination with project number B2112. Thank you.